Hi there, this video is on section 2.7, using the difference quotient formula to find instantaneous rate. I'm posting this video a little bit out of sequence because I do find this video helpful to watch and practice before doing some of the other sections, but you can feel free, of course, to do the homework in any order you choose. Okay, so before we talk about using the difference quotient, let me just remind you of what the difference quotient is. The difference quotient I covered in section 2.1. You can look at that video, and it looks like this thing right here. This can be simplified because the denominator, x plus h minus x, can be simplified by adding the x's together or subtracting x minus x. So the simplified version of this difference quotient, limit as h goes to 0, f of x plus h minus f of x is the top still, and the bottom is just h. So that's the simplified version that you'll find in textbooks and online. So where does that come from? Well, it comes from the fact that we're looking at a particular point on a graph. I just drew a random function here, and we're going to be choosing a point, an objective point right here, and we're going to call that point, well, we're going to call it x. And then we're looking for the rate or slope. And so we're going to choose another point a little bit away from x. Ideally, we would like to choose the point infinitesimally close to x so that we can find an approximation for the instantaneous rate. So we would choose some point like super, super close, but due to limitations of eyesight and physical pixelation, I'm going to draw it a little bit further, but we're going to sort of pretend that ideally that these 2 points are infinitesimally close. We want this distance to be basically as close to 0 as possible. The distance between x and x plus h. Okay, so just finishing off this little review, if x is the input, then the output, according to this formula, is just called fx. And likewise, if the input is x plus h, the output is called f of x plus h. And then if I just do the y2 minus y1, the change in y, that's the top part, fx plus h minus fx. And if I do the change in x, that's the bottom part. That's this part right here. So x2 minus x1. And that's how the difference quotient formula comes about. Again, we want these two values of x to be as close to 0 as possible. And so what does that mean? We mean that x plus h minus x should be as close to 0 as possible. In other words, we want h to be as close to 0 as possible. The difference between the 2 points should be as close to 0, or if subtracting the two distances should be as close to 0. You'll notice that these two algebraically are identical, once again, just by combining the x's together. Now, there's an alternate version to the difference quotient that I'll review right now because you will see that sometimes in the book and online. And so I'll just show you the alternate version. So this version is the one that I typically use, but there's an equivalent version, not necessarily better or worse, that you will see. And some people like this version better. It's a little bit less algebra simplification up front, but there's a little bit more algebra simplification later on. So it's a little bit of trade-off depending on your preferences. So let me just quickly show you the second difference quotient formula, this one right here. What they do is they relabel the axes, basically. Instead of x and x plus h, they give them different letters. So let me erase this stuff, and I will show you the new version, or the alternate version, I guess you should say, of the difference quotient. So the first thing, which can be quite confusing if you're trying to use both of these things, is that the first objective point, where we're trying to find the instantaneous rate of change, is called A. So we're no longer calling that X. And even worse, the next by point is called X. So we are choosing to look at A, trying to find the instantaneous rate at A, and we're choosing a nearby point, which is X. And of course, we want this distance to be as close to 0 as possible. Distances are found by just subtracting the values. So x minus a should be as close to 0 as possible. Algebraically, this is equivalent to x being the same as a, or infinitesimally close to the value of a. And then once again, we can just read off the y values with our just generic fx function. So plugging in a gives me fa. Plugging in x gives me fx. Then I do y2 minus y1, that's the top of the fraction. And I do x2 minus x1, that's the bottom of the fraction there. And then notice that we no longer have x going to 0. We have x getting extremely close to a. So the limit, if I zoom in here a little bit for people to see, the limit of this alternate version is x is getting closer to a, as opposed to the previous one where x was, or h was getting closer and closer to 0. So I'll demonstrate both of these difference quotient methods today in the video for you to sort of see them in action, and then you can choose whichever one you want to use going forward. All right, a little just vocabulary issues. This difference quotient that I'm explaining here, it finds the instantaneous rate of change at a specific point. It also finds the slope of the tangent line to the function at a specific point, and it also finds what's called the derivative at a specific point of that named function. I mention this because you will see quite often throughout the book and other sources where they'll say, oh, find the instantaneous rate, and you do that by using the difference quotient. Or they may say, find the slope of the tangent line at a particular point, and you use the difference quotient to find that. And oftentimes you'll be asked to find the derivative at a point, and that will also be the difference quotient. So they use different descriptions, different words, and they're all found by using the difference quotient. Okay, so let's do some examples so you can see these in action. Just zoom in a little bit and recenter this. Okay, so my first example here, I want to find the slope of the tangent line of a particular function at a particular point. The function is x squared plus 2x plus 5. The point is x equals 1. So finding the slope of the tangent line is found using the difference quotient. So let me do the difference quotient that I have used before. This is the h going to 0, f of x plus h minus f of x over h. Okay, so that's our just sort of typical difference quotient that you'll see and that I've used before. Okay, so all we have to do now is plug stuff in and do a bunch of algebra. Notice that we have been told that x is equal to 1. So we know the value of x. There's an x there, and there's an x there. So I'm just going to rewrite this thing since I know the value of x. So this becomes f of 1 plus h minus f of 1 over h. All right. Sorry, I'm just trying to clean this up so it looks a little prettier there. Okay, we're going to use the function to find these function values. So I do have my function right here. I'll make a little t-table. And this is x squared plus 2x. I got to move me somewhere else. Plus 5. And then I can plug in the number 1. And that becomes, well, 1 squared plus 2 times 1 minus 5, which is, oh, it's plus 5, sorry. 1 plus 2, I think that's 8. And then I can plug in 1 plus h. And I'm just plugging in these numbers for the x values. So 1 plus h is the next thing I'm going to plug in. And according to my little formula, that's 1 plus h squared plus 2 times 1 plus h plus 5. I'm going to simplify this. I have to use my algebra by multiplying this out. Remember to distribute or FOIL or however you remember to simplify these things. So I get 1 squared plus 2 times h plus h squared. And then this one's just a normal distributive property. So 2 times 1 is 2 plus 2h. And then we have this plus 5 at the end. I'll combine like terms. There's nothing that's similar to h squared, so I'll just write that down solo. There's a couple of h things. There's 2h and 2h. That gives me 4h. And there's three numbers, 1 squared plus 2 plus 5 gives me a total of 8. So there's my f of this right here. Right here is f of 1. That's the function evaluated at 1. And right here, this is f of 1 plus h when I plugged in 1 plus h into the function. All right, so let's go ahead and put the stuff into the formula. So f of 1 plus h is h squared plus 4h plus 8. And then minus f of x, or f of 1, which is 8. You know, I'm just going to put some parentheses around here just visually. That's the first thing minus the second thing. The parentheses aren't doing anything, but just emphasizing that it's the f1 plus h minus f1 thing. And here's my h right there. Please note, some people are a little bit just like plugging in numbers for x because x is a variable. You can see x having different values here. However, in the difference quotient, x is not a variable. The only thing that is changing values is h. H is getting closer and closer and closer to 0, 0.01, 0.001. H is the variable in the difference quotient. X is just a fixed value, a fixed point. So we can plug in numbers for x. We can't really plug in numbers for h because h is the variable. So just kind of keep that in mind if you're wondering about like x and the variable and stuff like that. All right, so I'm going to simplify this. Yes, I do have to keep writing the limit as h approaches 0 every time until I actually compute the limit. I am contractually obligated by the math police to reduce your score if you forget to write the limit until you actually take the limit. So beware. My plus 8 minus 8 add to 0, so I get h squared plus 4h on the top. On the bottom, I just have h. And once again, I'll need to simplify this. There's different ways of simplifying it. Distributed property or factoring are the two most common ways. I've been using distributed property in previous videos more often, so I'll use factoring this time, just so you can see that. The top has a h that's common, so factoring out an h on the top, or dividing by h for each of these things, gives us this expression, h plus 4. We have h on the top, h on the bottom. H divided by h is 1 over 1. And multiplying or dividing by 1 does not affect a value. So those ones essentially just get absorbed or disappear or cancel, as I've heard many people say. But they just get multiplied. So we have h plus 4 on the top, and we don't have anything on the bottom. Now, we know h is supposed to be infinitesimally close to 0. H is supposed to be like 0.00001 or 0.00001. So we have something here which is essentially infinitesimally close to 0 plus 4. Something close to 0 plus 4, infinitesimally close to 0 plus 4, has a value of 4. So 4 is the answer to the difference quotient, and that is right there. That is the slope of the tangent line to the function that we were given at the point where x equals 1. I know that's kind of a mouthful, but that's kind of the description of what we just found. We found the slope of the tangent line to a particular function at a particular point. Okay, so one more aside. Some people think about, well, you know, we plugged in this h being 0 thing, and we got 0 plus 4 is equal to 4. Why don't we just do that earlier? I mean, why do we do all this algebra stuff and then plug in 0 near the end? Why don't we plug in 0 early on? And the answer is you're welcome to try plugging in 0 on. You're just not going to really get a result. For example, I'll just choose this one right here. If I plug in 0 in for the bottom, immediately you can see that we have a division by 0 problem. And at this level of mathematics, we're not supposed to like run away and say, oh my gosh, we divide by 0. We should abandon this problem. We need to further investigate what's happening. In this particular case, if you plug in 0 for h everywhere on the top and the bottom, you will get 0 squared plus 4 times 0 plus 8 minus 8 on the top, which is 0 on the top and 0 on the bottom. And 0 divided by 0 is called indeterminate, which means we need to do more mathematics, more investigation to discover what it is, what it's equal to. So we just have a non-zero number on the top and 0 on the bottom. We're going to find out that it's always undefined and usually some version of infinity. But if you have 0 on the top and 0 on the bottom, we really don't know. It's called indeterminate because we can't determine it. But we can actually, if we do a bunch of more math work and investigation. And in fact, in this case, we determine the value is 4. So that's why you have to kind of wait until you do a bit of algebra where plugging in 0 actually gives you something which is determinable. All right, some vocabulary, some notation here. So we did find the slope of this tangent line, and there's 2 ways of writing this. There's many ways of writing it actually, but 2 ways that are most typical for Calc 1 students. This one here on the left, which looks like a fraction, dy over dx, like change in y over change in x. That line means evaluated at. So this is the change in y over change in x evaluated at x equals 1. So that's the instantaneous rate or the slope of the tangent line at the point where x equals 1. And then we have this other version over here. This is f with a little like hash mark, a little like prime, it's called, parentheses 1. This is not the value of the function at 1. This is the value of the tangent line, the slope of the tangent line, or the instantaneous rate when x equals 1. Now, your textbook author and professional mathematicians and calculus students who have gone well beyond Calc 2 tend to use the one on the right, but this is really a mistake. This is not a very good notation. I really recommend strongly that you don't use this. The main reason is that there's a bunch of formulas in this class, as well as Calc 2, which do not work with this little hashtag prime notation, but definitely work very, very well with the fraction dy over dx notation. So even though it looks like it's, it definitely takes longer to write, looks more complicated, it is a very good investment in time. It's going to make the rest of your calculus journey much, much easier. If you do get attached to this primey thing, my experience is people, tend to have a hard time unlearning things. So I would just recommend learning this regular notation. And then later on, when you become very, very, very comfortable with all the complicated formulas, then you can use some abbreviations like the calculus textbook authors do. All right, so let's try another problem. Remember, if I have not mentioned it, feel free to pause the video and try any of these problems. Like this is a very similar problem to the one we just did. Find the slope of the tangent line of this particular function at a particular point. It's great to practice stuff. If you think you got it, then sort of go through the steps without just watching my video, be actively involved. And that will help you really understand how much you know and if you get stuck on any steps, where you got stuck. Okay, so find the slope of the tangent line at fx equals x4 minus 5. For this one, I'll use the alternate version of the difference quotient formula, just so you can see that one in action. So the alternate version is x getting closer and closer to A. A is my objective point. That's the location that we're trying to find, right? So again, they switched up the variables. A is the one we're trying to find the instantaneous rate or the slope of the tangent line, and x is the nearby point. So, oops, I'm going to zoom in again. So again, a little bit, you have to remember the notation a little bit. All right, so on the top of the difference quotient, we have fx minus fa, and the bottom one we have x minus a. One of the reasons I don't use this formula as much is because you do have to remember that they've switched around the variables. So when they say at the point where x equals 3, remember our objective point is called a. So if we're using this version of the difference quotient, that means a is equal to 3. x is the nearby point. It's like the x plus h, right? The a value is our sort of point that we're trying to find. So when we do a little table of values, right, with our x and our x squared minus 5, we have an a value, which is, well, I'll rewrite this thing so you can see it. So the a value is 3. So we do the limit as x approaches 3. Remember, a has a value of 3. And we do fx minus f3 over x minus 3, right? Notice the objective point is the a value, even though they wrote it as x. That's just the way, the communication works in math. So the two things I need to write down here are 3 and x. Those are the two different x values. I plug in 3 into this formula. I get 3 squared minus 5, which is 4. I plug in x into this formula, and it's the same thing. It's just x squared minus 5. So you're seeing one of the benefits of this formula is that it's actually much easier to do the algebra, certainly here in the beginning of the problem. All right, so x approaches a means x approaches 3. Fx is our x squared minus 5. And then our f3 is 4. And once again, I'll just kind of emphasize this for people who need a visual reminder. Those are the two things that we're subtracting on the top. The parentheses are doing nothing. If you don't want the parentheses, certainly don't put them. There we go. X minus a. Okay. And we will just combine these things together on the top. X squared minus 5 minus 4 is x squared minus 9 over x minus 3. You'll find out that plugging in 3 isn't going to work. 0 in the denominator. You actually also get a 0 in the numerator. So we need to simplify this algebraically. So this is a little bit more complicated simplification than the previous problem. And because we're using this other formula, that's usually what happens. The top can be factored as a difference of squares. So we're going to use sort of the two parentheses factoring method. It's x minus 3, x plus 3. That's how that x squared minus 9 factors. And you can see we have a factor on the top and a factor on the bottom. X minus 3 divided by x minus 3 is just 1 over 1. The ones don't matter. So we get the limit as x approaches 3 of x plus 3. X is getting infinitesimally close to 3. So this is getting super, super close to 3. So the limit becomes infinitesimally close to 3 plus 3, which has a value of 6. So 6 is our slope of the tangent line at that particular point. All right. So that's using the alternate formula. And a little bonus here. They don't ask this very often in this section in the homework, but they will ask it later on. What is the equation of the tangent line? We found the slope of the tangent line. That's not the equation, that's the slope. How do we find the equation of the tangent line? Well, a tangent line is a line, just like any other line. You can use the formula to find the equation of a tangent line. I'm going to use the y minus y1 equals mx minus x1 version. We need an xy point for this thing. We do want to use the number 1 because that's our objective. So we need to know, we need to use the number 3 because that's our objective, right? We want to know what happens when x equals 3. And we know when x equals 3, the y is equal to 4. So we have a point 3 comma 4, and we have a slope equal to 6. And so I can just plug that in. The y value is 4. And the x value is 3. And it's considered good manners to write the 4 on the other side. And if you wish, you could multiply this out as well. Up to you. Up to you. All right, so that would be the equation of the tangent line to the function x squared minus 5 at the point where x equals 3. All right, so let me show you visually about what's going on here. Let me get rid of this stuff just for a moment. Oh, here's my x squared minus 5 graph right there. And if I type in the equation of the tangent line we got had a slope of 6. The x value was 3. And then we had a -4 on the other side that we moved over, +4. So you can see that that is the equation 6x minus 3 plus 4 that I typed in to Desmos here. And if I zoom out, you can see there's the parabola and there's the line. There's the two of them. And they're definitely different. You can see that they are not the same. But my objective point is when x equals 3. And if I zoom in really close to there, uh, they're both there. The line and the parabola are both there, but they're basically indistinguishable. They look identical, right? They're infinitesimally close to each other. And that's the idea behind the big idea behind calculus is that if we kind of zoom in a bit, then on this sort of microscopic level, complicated functions, whatever functions you have, are going to be basically indistinguishable from a tangent line. So we can use all these tangent lines to describe a function instead of the function itself. Much easier to work with simple line equations than complicated functions. I'm using an x squared here, but you can imagine sine, exponential, or worse kinds of functions, which are typically difficult to deal with. Okay, and by the way, the first problem was a similar kind of thing. Here was the parabola from the first problem. I didn't calculate it for the first problem, but there's the tangent line for the first problem we did. And once again, you can see that the tangent line becomes indistinguishable from the function when you get infinitesimally close to the objective. And the first problem was x equals 1. So we get infinitesimally close to x equals 1. You can see the two of them are virtually identical. Okay, so that's visually what's going on there. Yeah. All right, we'll do a couple more problems here to end the video, just to kind of see what's going on here. But that's essentially what this video is about, is just using the difference quotient to find the slope of the tangent line or the instantaneous rate, or we used it actually to find the equation as well, given that we were able to locate the point that we needed to use. All right, so here's the last couple problems. All right. So part C says find the slope of the tangent line to the point fx equals x squared minus 5 at the point where x equals a. Hey, wait, wasn't that the problem we just did? The last problem we did said at the point, whoops, at the point where x equals 3, and oops, when x equals 3 right here. And this new problem says where the point where x equals a. So the only thing we've done is we replaced the number x equals 3 with the number x equals a. So we've just basically made it a little bit more abstract by not using a particular number, but by using this, sort of abstract a thing. But the process, the mathematical steps are going to be identical. Everything we did before, we're going to do the exact same way, right? So we're going to do the limit as x approaches a, f of x minus fa over x minus a. And we have our table of values. Our objective value is a, and our second point is x. But our equation is just x squared minus 5. So when I plug in a, I get a squared minus 5. When I plug in x, I get x squared minus 5, just like that. So I'm just going to put those into the formula. Fx is x squared minus 5. And then Fa is, fascinatingly enough, a squared minus 5. And the bottom is x minus a. All right, so similar steps, a little bit more letters to write down, but just follow the algebra and you'll do fine. Combine the things together on the top. We have a -5 minus a -5, which is, 0. So I'm left with x squared minus a squared on the top. And on the bottom, left with x minus a. I can factor the top. This is the difference of squares that factors to x minus a, x plus a. The bottom is still x minus a. I have a factor on the top, a factor on the bottom, which are identical. So those become 1 and 1, but multiplying or dividing by 1 does not do anything. So this is the limit as x approaches a of x plus a. X is getting closer and closer and closer to the value of a. So this thing becomes basically exactly indistinguishable from a, infinitesimally close to a. So we get a plus a, which is 2a. So 2a is the slope of the tangent line at a point x equals a that I haven't specified. So this is true for x equals 1, for x equals 1, x equals 2, x equals 3. At any value of a that I specify, this is true. Particularly, I can plug in any value of a, right? So I can plug in a equals 1. So that gives me the slope is equal to 2 at the point where x equals 1. But we actually just did the problem where a is equal to 3. That was the last problem we just did. Get this back here. And if I plug in a equals 3 as an example, then I get the slope is equal to 6. Which is, of course, what we found on the previous problem. When you plug in the 3 in the beginning and then do all the math, we got a slope of 6. If you just plug in a and do all the math, you get an answer of 2a, which you can plug in 3 to get 6. But the advantage of this version, where I plugged in a, is that if they ask me to find the slope of the tangent line at the point where x equals 4, I don't have to redo the problem. I know the answer is 8 because now my new objective point is a equals 4. So for a different value of our our objective point, our a value, then it's just as easy to find the slope. So we if we can do this in general with a letter instead of a number, it gives us a very powerful formula that very quickly allows us to find any slope of any tangent line, whatever the point is we want to specify. All right, let's do one that's algebraically more complicated. This one I'm going to do right here involves some fraction. So I'll just do -1 over x. And I'm going to do, again, the point where x equals a. Not giving you a specific number, but we're doing it in general for the letter a. All right, I'll go back to our standard, difference quotient formula with the h approaching 0, fx plus h minus fx over h. And I do make my little table. I'll make it over here, I guess. So this is the previous problem. So I have x as my input, and my output is -1 over x. My 2 points are x and x plus h. I plug in x, nothing really happens. I still get -1 over x. I plug in x plus h, and I get -1 over x plus h. So those are my 2 y values. Oh, I forgot to say x equals a. So let me put an a in there instead. So let me put an a here, and that will be -1 over a. And let me put an a here, and that will be -1 over a plus h. I mean, it's just a letter; it doesn't really matter. But I'll follow the rules according to the directions according to the problem. Well, let me first write this here just to clarify. We want x to be closer and closer to a. So I'll just write that in there. A plus h, f of a over h. So I've just substituted a, and for x, it's the same problem, just with a different letter. All right, so let's plug it in. F of a plus h is -1 over a plus h. And f of a is -1 over a. -1 over a. So we got a minus, which will end up being a plus. And then on the bottom, we have an h. So you can see visually, this looks more complicated. You have fraction minus fraction in a fraction. I just demonstrate this one so you can kind of see the algebra for fraction problems. There's different ways of simplifying these fractions. I'm just going to try to rewrite this in a more sort of easier to write way. We have a negative 1 over a plus h, and we have a minus 1 over a, so that's plus 1 over a. That's the stuff on the top. When I divide by h, dividing by h is the same as multiplying by 1 over h. So I'm just going to write this way so it's a little easier to write and sort of figure out. All right. Again, there's many ways of simplifying these things. Use your favorite technique. All right. So to simplify this, I'm going to combine together these fractions inside the parentheses. I'll do that just by finding a common denominator. So my fraction here, I'm going to have to multiply these, top and bottom to get a common denominator. So I'll multiply by a on the top and bottom for this guy, and I'll multiply by a plus h on the top and bottom for this guy, so that they both have a common denominator of a plus h times a. So our common denominator would be a plus h times a. And then on the top, I have negative 1 times a, which is negative a. And then I have plus 1 times a plus h, which is a plus h. So those are the two fractions combined together on a common denominator. I still have my times 1 over h at the end. So remember that, or remember the big divided by h sign. Still writing the limit until I actually do it. The top simplifies here. Negative a plus a is just h. So I get h on the top. The bottom, I can multiply it if I want. I don't have to. It typically doesn't help to multiply at the bottom. It's not wrong. But I'm going to leave it unmultiplied out just to demonstrate that it doesn't really do much if you don't multiply it out. All right, now we have multiplication by h and division by h. So here's multiplication and division by h. So those become 1. And multiplying and dividing by 1 don't do nothing. So this becomes the limit. H goes to 0. Top is just 1. The bottom is a plus h times h. Now I am going to let h be a plus h times a, excuse me. I knew I had made a mistake there because there was an h down there, and that was not supposed to be there. So the a is what I should be writing. Just made a little reading error there. There we go. All right, so now I'm going to let h be infinitesimally close to 0. So this guy right here should be really, really close to 0, indistinguishable from 0. And so what I get is 1 over 0 plus, excuse me, a plus 0, because h is going to 0, times a. All right, hopefully that's not too confusing with my little verbal snafus there. That becomes 1 over a plus 0 is just 0, just a, and a times a is a squared. So my answer is 1 over a squared. So that right there is the slope of the tangent line at any particular point x equals a. So if I'm looking at the point where x equals 3, the slope would be 1 over 3 squared, 1 over 9. So that's the generic formula for the slope of the tangent line at a point, whatever x equals a. I've just demonstrated, by the way, in these last two examples, in example C and D, where we just used a generic point x equals a. This is what mathematicians refer to as the derivative. So not the derivative at a point, which means we specify the x value. This is just called the derivative in general. So just say the derivative and leave off any other moniker, because we can use this formula to find any slope of any tangent line in any instantaneous rate, as long as you give me the specific value that we're looking for. So whatever value of x we're looking for, you throw it into the formula, and that will give you the slope. That formula, the formula that gives you the slope at any particular point, this is at any point x equals a. So that formula there is called the derivative. So you'll see a lot of times the derivative, that is the formula that enables you to find the slope of the tangent line at any particular point that you want to specify. All right, I know this video is running long, and I'm just doing some more examples here. So if you got the idea and you feel very confident in your algebra, I'm just doing more of the same. I'm going to do one with square roots in it because some people don't remember how to simplify square roots in complicated problems. So I'm just going to demonstrate the square root one as my last final example so that if you come across that in the homework, you can refer back to this video. All right, so we have square root 8 times square root of x. Let me use green this time. Again, you can use whichever formula you want. Maybe I'll use the x approaching a one just for a second go, just so people can see it more than once. Oops, x approaching a. And the top becomes fx minus fa. And the bottom is x minus a. This is our alternate version of the difference quotient. Again, feel free to use whichever one you wish. All right, we have the point x equals 9, which according to our formula, the alternate version, this is the a value. Remember, they switch up the letters on you just so it's very confusing. So when I have my table of values, the first value we have here is 9, and the second value we have is x, and our function is 8 root x. You can see this in the formula. If you sort of imagine that you are sort of finding x getting closer and closer to a, and we know that a value is 9, then this becomes limit as x approaches 9 of fx minus f9 over x minus 9. So that is one of the things just you have to keep. Remember, is the objective point, what they give you is the a value in this alternate version. So that's where the 9 comes from, and the x, there's the 9, and there's the x, right? So those are the two input values we put, and we put into the formula 8 times the square root of x. Looks like I've written this a little sloppy, so let me try this a little better here. 8 root x. All right, I plug in 9. I'm going to get 8 times the square root of 9, which is 8 times 3 and 24. When I plug in x, I just get 8 root x. Nothing exciting there. All right, so let me put this into the formula. Got our limit thing that we have to continue writing until we actually take the limit. Fx is 8 root x. F9 is 24. And the bottom we have x minus 9. All right, so we now have to figure out what to do with this limit, and we can't plug in 9 directly, at least not right now, because we get 0 in the denominator. We actually also get 0 in the numerator, which in some sense is good. We know this is indeterminate, and we can simplify it and hopefully get a better version that we can then substitute values that are infinitesimally close to 9. So one of the things that we're going to do to simplify complicated square root problems is we're going to use the conjugate. The conjugate is when you have two things added or subtracted together that can be dramatically simplified by squaring them. Square roots can be very simple, can be dramatically simplified by squaring them. Other things, for example, sine and cosine, are very difficult to combine together, but sine squared and cosine squared can be easily combined together. There's different versions, but you have things that can be simplified by the squares instead of the actual object themselves. The conjugate will really help. So what's the conjugate? Well, it's the exact same square root thing or whatever you're trying to simplify, but with the sign changed. So in this case, it would be 8 root x plus 24. That would be the conjugate of 8 root x minus 24. And we're simply going to multiply the top and the bottom by that conjugate. All right. On the top, this is, well, we're going to multiply it out. So 8 root x times 8 root x is 64x. Then we have 8 times 24. I didn't prepare that ahead of time, so let me do that now. 8 times 24. That's 192. So 8 times 24 is 192, so that's plus 192 root x. And then I have the minus version of that also. So I have minus 192 root x. So those are going to add to 0, which is kind of nice. And then lastly, I have 24 times 24. I have to use a calculator for that as well. And that's 576. All right, and then on the bottom, I have quite a bit of mess here. X minus 9 and 8 root x plus 24. Once again, it's unlikely that multiplying out the denominator is really going to do much. It just, you'll see that over and over again. I did forget my little limit symbol. So I'm going to have to go back there and insert that. Otherwise, I will lose points. All right, so what do I do now? Well, I got to continue to simplify. The top, I combined those two things together. And what I'm left with is 64x minus 576 on the top, and x minus 9 and this square root thingy thing on the bottom. So now, yeah, you're like, what do I do now, right? Well, you remember that, these problems should work out some way. So let's see if we can try to factor the top. The top has a couple big numbers in it, 64 and 576. Let's see if those numbers can be divided. Let's take 576 and divide by 64, see if they have something common with them. Look, 576 divided by 64 is 9. So that means I can factor out a 64, and this becomes x. And remember that 64 times 9 is 576, so that just becomes 9. And now you may be seeing that this is working out after all. After we factored it, we have a sort of factor, a thing on the top and a factor on the bottom that are identical. And so we know those divide to equal 1. And so now I am left with, come on, pen, limit as x approaches 9. On the top, I just have 64. On the bottom, the x minus 9 part got divided out. So I'm left with 8 root x plus 24. And at this point, I am able to safely substitute values that are infinitesimally close to 9. So this thing right here becomes infinitesimally close to 9. And now I can write this without using the limit, because we can find the limit by saying this is basically identical to 9. Just like that. And 8 times square root of 9 is 8 times 3, which is 24. So I get 64 over 48. We do want you to simplify things mathematically, so I can simplify these things. You can try to find easier ways to simplify this, but I'm just going to divide the top and bottom by 2. You don't have to be fancy about it. If you want to be fancy, it's fine. I'm going to divide by 2 again. Divide by 2 again. Divide by 2 again. 4/3. Right. Again, you could do it in fewer steps. I'm just saying you don't have to. So 4/3 is the slope of the tangent line of this given function at the given point. So the function here we have was 8 root x, and the point was x equals 9. All right, so those are a whole bunch of examples and sort of background information about using the difference quotient to find the instantaneous rate of change, aka the slope of the tangent line, aka the derivative at a point. Hopefully you found this video useful, and you will let me know if you have any other questions or need help with anything. All right, please enjoy your day.